In this video, we're going to take a look at solving exponential and logarithmic equations. And the way we're going to do that is by looking at the similarities and the operations that we see between these two expressions that you see here. So what do we mean by that? By now you should be pretty familiar with exponentials. We've got y equals b to the x. So you know what that means. That means I'm just taking b and multiplying it by itself x times. Well, if I'm going to try to solve this, I don't really have a good way to get x out of this exponent up here. In other words, I can't really divide by anything or use some other exponent rule, subtract, square roots. Nothing will work to get x out. And so that's why we use logarithms. A logarithm really is nothing more than a function that's an inverse of the exponential. As a matter of fact, you can think about the logarithm as the exponent itself, simply because we see x is the exponent and x is equal to this log. So let's take a look at this real quick and recognize that this is really the same thing. These two things are the same thing, except just written differently. All the pieces are here. We have the base, which is the number that's being raised to the power, which is the same base over here. In this case, x is our input and y is the output, and here y is the input and x is the output. And that's something that we know is typical of inverse functions, exchanging the input and the output. So the first thing I want to show you here is maybe one of the simplest ways to solve exponentials using logs or vice versa, and that's really by just matching up the pieces into something that is familiar enough that we can solve it without too much additional work. For example, if I had the expression 100 equals 10 to the x power, how could I solve this for x? Well, the easy way to do this is to just recognize that x is going to be 2 because 10 to the second power, or 10 squared, is 100. And so that means x is equal to 2. Now if we compare that or relate that to the logarithmic expression here, what this is saying is that x is going to be equal to the log to the base 10 of 100. Okay, so here y was 100, b was 10, and x was 10, x rather. And so here again, x is x, b is 10, and y is 100. So all I've done is rearrange according to the template, if you will, that I have here. Well, this is just a number. I can take the number 100 and punch that into the calculator, hit the log button. Remember that log on the calculator is the same as log to the base 10. And that's going to give me the same answer, x equals 2. I can also use this approach to solve a logarithmic expression. For example, I can figure out x equals log to the base 2 of 8. And the way I can do that is to rearrange this into an exponential. 2 is my base, x is the exponent, and 8 is y, the answer. So now I just need to know again what value of x is going to give me 2 to the x equals 8. And that I know is 2 to the third power equals 8. 2 times 2 times 2. Well, that's all well and good, but things do get more complicated than that, of course. And so let's take a look at something like 3 to the x plus 5 power is equal to 3 to the 7th power. How could we solve this? Well, we could go through a lengthy process here, which will be similar to what we'll look at towards the end of the video, but what I want to show you here is the easy way to do this one is to recognize that we have the same base. And so if 3 to some power is equal to 3 to some other power, then obviously those two powers have to be equal to each other. And so this is just a matter of setting the exponents equal to each other. And in this case we see x is equal to 2. This is what's called solving by the same base method, or common base. We can also apply this to logarithms. We could do something like log to the base 8 of x plus 1 is equal to log to the base 8 of 6. So once again, I'm plugging the same thing, I'm plugging something into the same function, I should say, and getting the same answer. And so whatever I'm plugging into that function should be the same thing. So if I set those equal, I should get x plus 5 satisfies this equation right here using the common base or the same base method. Well, even that was a little bit more complicated than what we had before, but still not as complicated as things obviously can get. And so let's consider another example. Log to the base 3 of x equals 5. Now there's a couple ways to do this. We could go back to our expression up here, our definition, and rearrange things a little bit and say that our answer, x, just taking the place of y in this case, is equal to the base raised to this power. X equals 3 to the 5th power. So we could do it that way. But let's take a look at another method that will help us if things are a little bit more complicated than this. What we're going to do is to raise 3 to the power of both sides. And the reason for that is as follows. If I take 3 and raise to the power of both sides, I see I have a common base here, which is 3, which would give me this expression here. But more importantly, if you look at this side here, this begins to look a little bit like an inverse. I have a number raised to a power, which is a logarithm. I have an exponent, which is a log. I'm exponentiating a log. So that should give me an inverse, which means that if I plug in x into that thing, my output should be x. So in other words, let's take a look at this real quick before I go on, just to be sure that we understand this. I can take y equals b to the x, and I can replace x with this, log to the base b of y. So you see that if my base is the same from the exponent base and the log base, then whatever's inside the logarithm is going to be the answer. So here I have the same base, which is 3. Whatever's inside the logarithm becomes the answer. And on this side I have my 3 to the 5th power. And so you can see that that gives us the same answer. And finally, we can use a similar method to solve exponentials. So let's do something like 6 to the x equals 27. Okay, what number can I raise 6 to get 27? Well, if I raise 6 to the first power, I get 6. If I raise 6 to the second power, I get 36. So it's probably going to be somewhere between 1 and 2, but not a number that I'll be able to guess off the top of my head. So how can I solve this? Well, again, I'm going to use this inverse relationship and take the logarithm of both sides. Okay, and in doing this, what I'm going to do is to recognize that this is the exponent property of logarithms, which says that I can rewrite this by taking the x out front and just leaving this on the inside. So this is now x times log of 6, and I have log 27 on this side. And so if you notice, once again, this is just a number. This is just a number. I'm going to divide both sides by log of 6. That allows this side to go to x, and over on this side, log of 27 divided by log of 6 gives me an approximate answer of 1.839 and some more stuff. So you remember when I first set this problem up, I said that it was going to be somewhere between 1 and 2, and sure enough, it's between 1 and 2. In any case, once again, we're going to take the log of an exponent to get the exponent out of the expression to where we can work with it.